So for tonight, we will have the next 30 minutes talking about the intro to or the introduction to mass transfer. So unit operations processes here that are relying heavily on the fundamental principle of mass transfer. Now, so far we have learned that heat is transferred if there is a temperature difference in a medium, which reminds me of your quiz. A majority of you, when asked what is the driving force for heat transfer, you answer temperature. The driving force is temperature difference, not temperature. Temperature is just a process parameter. So similarly, we have to know here what is the driving force if mass is to or mass transfer is to occur between phases or maybe between a solid and a liquid phase. So that particular driving force is the, again, difference in what? In concentration. So if heat transfer will occur by virtue of temperature difference, in the case of mass transfer, it will occur by virtue of concentration difference. Now, mass transfer is mass in transit as a result of a difference in concentration of the species that are present in a particular mixture. Now, when we speak of two phases of different compositions, and when these two phases are brought into intimate contact, component transfer may occur from one phase to another or vice versa. And normally, the phase that has a higher concentration will have that particular, shall I say, force that will lead to equilibrium later on when the concentration of the two phases are already equilibrated. And as such, we say that the rate of transfer of one component from one phase to another is already the same or equal. But that does not mean that the transfer already stopped. It's just that the rate of transfer from one phase to another and from that phase where it was transferred back to that other phase where it came from is just the same. Just like the concept of reversible processes when they are already equilibrated. We say the rate of the forward reaction is equal to the rate of the reverse reaction. So it's the same thing with equilibrium already existing in phases that have established it. So mass transfer will only occur if they are not yet equilibrated. Now, this is the physical basis. So that is the difference in the concentration of mass transfer operations. The mass transfer operations that we will be discussing in the future, and we'll be starting with the next in a couple of weeks, will be diffusion, gas absorption, drying. So all of those will include mass transfer. But in the case of drying, it's now a case of simultaneous heat and mass transfer. Now, if the two phases are in contact, so the two phases wherein mass transfer is to occur for a sufficient period of time, they will eventually reach equilibrium. And thereafter, there is no longer a net rate of components or a net transfer of components between them, meaning there's no net transfer, but there is still transfer. It's just that the rates are equal. Now, in most cases of interest to mass transfer operations, the two phases are only partially miscible. And so that in equilibrium, there are still two phases that can be separated from each other. In the case of later on, you will learn about liquid-liquid extraction in detail. And you will know that it is necessary at some point that the phases that are contacted are only partially miscible. Usually, these two phases that are partially miscible have different compositions, and these compositions are also different from those of the phases at the time of initial contact. So there will never be any mass transfer if the compositions in the first place are the same thing with concentration. So their composition need to be different. Therefore, in the case of mass transfer in this particular scenario, the one that is being referred to in here is between liquid phases, the relative quantities of the components that are transferred between the phases are different, so that the separation between them is achieved. So we say that the quantity that being transferred by one phase to another should never be equal to the quantity that the receiving phase is transferring back to the giving phase. So they should never be in equal quantity. properties. That way, we will never have what we call equilibrium. But at some point later on, when we have already multi-stage unit operation processes employing these mass transfer operations, there would really be equilibrium. And we need to assume equilibrium. That way we can effectively design our equipment. If not, then we won't be able to design the equipment that needs to, of course, uh, facilitate the given reaction. Under appropriate conditions, repeated contact and phase separation can lead to almost complete separation of the components. The physical basis for the separation processes using multi-stage equipment is the difference in phase equilibrium compositions. Again, having to do with equilibrium condition and composition. The unit operations thereon that we're going to learn are pertinent to separative processes, or what we call separation processes, that depend only on differences in physical properties and not on chemical behavior. Now, I'd like to emphasize this. The unit operations that you are studying, starting momentum transfer until now, and even in separation processes, and even in particle technology, that does not involve, or they don't involve chemical reactions. They are simple physical processes, transfer of a component to a different phase, or transfer of energy from one phase to another. Now, these processes are either based on a difference in the equilibrium phase composition or a difference in the mass transfer rate of the mixture of components, referring to the separation processes that is mentioned here in the second bullet. Now, of the separation processes that I have selected, because they will be again discussed later on and you will learn them in detail, is distillation. In my experience before, a good time for the coverage of the distillation process would be a term. What I mean with a term, it is good for the student to learn this particular concept probably in 5 weeks. If there's lesser than 5 weeks, then we expect that the student would really need to double time. If ever this particular topic is coupled with another unit operation process to study, it's because distillation is really vast in terms of application and in terms of the challenges in the design of the column itself. Now, this is the most widely used separation process in the chemical industry. And this unitary operation, or this unit operation, is also called fractionation or fractional distillation, even referred also to as reflux distillation. The separation of the constituent here is based on volatility differences, and it's always using the term differences. So the one that drives the process to happen is a difference, in this case, in the distillation in volatilities. So in distillation, a vapor phase comes into contact with a liquid phase. And take note, the vapor is actually produced from the liquid phase. And there is a mass transfer from the liquid to the vapor and from it to that. Liquid and steam generally contain the same components because your steam, your vapor, simply came from the liquid, but they are in different relative amounts. So I will not discuss into details the things of this because you will just learn them later on. This is just an overview. Now, the liquid is at its bubble point and the vapor in equilibrium at its dew point. I think you know what the bubble point is and the dew point is. There is simultaneous mass transfer of liquid by vaporization and of vapor by condensation in the process of distillation. So while the vapor is being condensed in the condenser, it's an auxiliary equipment for your column, your liquid is being vaporized in the still, or we call it the distilling column. The end effect is an increase in the concentration of the most volatile component in the vapor, or in the steam, and the least volatile component in the liquid. You will know the terms related to this later on in the topic of distillation. So I will share to you here a video on what is really happening inside the column for you to have an idea. But before that, I'd like to read what I have written here. So distillation in terms of application is widely used to separate liquid mixtures into more or less pure components. Now, just like in the case of the refining of crude oil. So we separate the different components of crude oil. As the components undergo a series of fractionation, they become more refined. And as they become more refined, they become more costly. So that is why the crude oil is cheap. Crude oil is cheap, but let's say gasoline, the premium gasoline with all the additives present on it is already expensive because of that. It has already undergone several fractionation processes. And aside from that, of course, the add-ons to it to enhance its performance later on when it's being used by our engines. So distillation applications have the widest diversity. So in the first example, pure oxygen used in steel making, rockets, and medical applications is produced by the distillation of previously liquefied air. So liquefied air undergoes distillation so that pure oxygen is the end product. And it's now being used by rockets. It's being used in medical applications. We know the hospitals are using oxygen. It's being used in steel making and so on and so forth. Now, crude oil, I have mentioned it already, is initially separated into several fractions such as light gases, naphtha, gasoline, kerosene, fuel oils, lubricating oils, and even asphalt into large distillation columns. So these fractions, so we refer to them now, these components are referred to as fractions, are further processed into finished products, and distillation is often used in the intermediate steps of obtaining this final product. If I may say, it's the main unit operation process that refines or separates from the crudest form of the raw material to the finest form that is being used in the market. So I'd like to show to you the video. Okay, I think you were not able to hear all the audio. There must be something wrong with the way I have copied the video. Anyway, let's proceed. So we go to the next separation process and discuss absorption and desorption. Now, desorption is just the opposite of gas absorption. So in gas absorption, there is the transfer of a soluble component of a gas phase to a relatively non-volatile liquid absorber. So your liquid absorber in the case of gas absorption forms as the or acts as a solvent, and the component of the gas is the one that is being taken out by this particular solvent. Now, desorption is the reverse process I have mentioned already, the removal of a component of a liquid by contacting that particular liquid by a gas phase. So this time, it's your gas phase that is acting as a solvent and your liquid phase as being the source of the component of interest. In the simplest case of gas absorption, the liquid absorber does not vaporize and the gas contains only a soluble component. As an example of gas absorption is ammonia being absorbed from a mixture of air and ammonia. And this is actually majority of the sample problems that we are going to discuss later on. So this particular air ammonia mixture is contacted with liquid water at room temperature. And since ammonia is water soluble, then it is being transferred into the water, while air is being inert to water, it remains insoluble. So we are able in this case to separate your ammonia, which is a contaminant from air, by simply using pure water. Now, water in the case of gas absorption being used as a solvent in turn hardly vaporizes at room temperature. In this case, we need to view the process as something in which liquid water remains as liquid. So therefore, the only mass transfer here is from gas phase ammonia to liquid solvent water. As the ammonia passes into the liquid, its concentration increases until the dissolved ammonia is in equilibrium with that in the gas phase. Once equilibrium is reached, there is no more effective mass transfer in this particular cited example. In absorption equipment, the liquid absorber is below its bubble point, so it's not about to boil, and the gas phase is far above its dew point. It's not yet about to condense. Another difference between distillation and gas absorption is that the liquid and gaseous phases do not contain all the same components. In the case of gas absorption, your components in the gas phase and in the liquid phase are, shall I say, not necessarily the same. Most of the time, they're not the same. But in the case of distillation, since your vapor is being produced from your liquid feed, then your liquid and your vapor phases have the same components, but not necessarily the same in composition. Now, thermal effects on absorption are due to the solution heat of the absorbed gas in contrast to the vaporization and condensation heats that participate in the case of distillation. Now, it's always a starting point when I discuss distillation and gas absorption that I always distinguish one from the other, or I differentiate one from the other. Because later on, when we design the equipments of these two, there is great similarity in the manner in which they are being designed. But as to the characteristics of the phases that are present during the process itself, they're very different. So they are to be treated very differently. Now, absorption involves the addition of a component to the system that is the liquid absorber. In many cases, the solute must be removed from the absorbent. Meaning, after gas absorption, since your liquid solvent already dissolved the component of the gas to itself, then after the process of gas absorption, there's a need to separate that particular dissolved solute that is in liquid form already in your gas. So this is what it meant here. Involves the addition of a component into the system. In many cases, the solute must be removed from the absorbent, referring to your liquid solvent. This removal may be done in a distillation column or in a desorption apparatus or in any other separative process. Now, desorption, the opposite of gas absorption, is desorption, or another term used is stripping, or extraction is the opposite. In this case, the soluble gas is transferred from the liquid to the gas phase because the connection, or rather the concentration in the liquid is greater than the equilibrium concentration with the gas. As an example, another example, ammonia can be extracted from an aqueous solution, meaning water with ammonia, by bubbling air through the solution. So this time, it's your gas, air, that is acting as your solvent. The air in the inlet contains no ammonia while the liquid contains it. There is then a transfer from the liquid phase or from water. We take out ammonia to the gas, which is the air that is being bubbled into it. Absorption and extraction are widely adopted in the chemical industry. So absorption and extraction are performed, most of the time they are performed in multistage equipment and to a lesser extent on continuous contact equipment. You will later on study this. They are most of the time in multistage processes. Now, I'd like to share to you a video again on gas absorption. Also called hours, designed to remove both particulate matter as well as gases. Contaminated gases sent into the tower. Inside the tower is a bed of special packing material. Nozzle sprays scrubbing liquid on top of the packing material, and the liquid works its way down the tower. As the gas passes up through the packing material, particulate gas molecules come in contact with the film of structure on the packing material. The contaminated liquid drains down through the packing material, past the packing support, and out through the bottom of the tower. Gas stream pours out through the top of the packing material, past the nostrils, and through a mist disseminated or exit the tower. So that's a very simple illustration of what's happening in a gas absorption tower. Majority of the operation is in the separation of a contaminant in the gas using a liquid solvent. So in the case of the example that was shown, it's ammonia being scrubbed off from the air ammonia mixture, okay, by using a liquid solvent. Now we go to liquid-liquid extraction. So this time, since it's liquid-liquid, then we expect that both phases are in liquid form. So a liquid mixture can sometimes be separated by contacting it with the second liquid solvent. So the components of the mixture are soluble to varying degrees in the sun. Ideally, the component to be extracted is solvent soluble and the other components are said to be insoluble. So in the case of liquid-liquid extraction class, your solvent need to be able to separate only or need only to dissolve the particular solute that it needs to take out. The other component in the mixture should be remaining insoluble to this solvent. Then the solute is the only component transferred from the initial mixture to the solvent phase. The initial mixture becomes refined as the solute is extracted from it. The solvent phase turns into the extract as it receives the solute. Now, in liquid-liquid extraction, we have this term, the product phases we call the extract and the raffinate. So the extract contains the solute that was taken out from the liquid feed, and the raffinate is the byproduct. So meaning all the rest of the components are in the raffinate phase. Now, in practice, all components are possibly soluble to some degree in each other, and separation is only feasible when the solubilities are sufficiently different. So again, take note, in the case of liquid-liquid extraction, the driving force is difference in solubilities. So your solute has to be dissolved or should be soluble in your solvent. In any case, the non-extracted inert component must be sufficiently insoluble to form two extractable phases. And these two extractable phases are the ones that I have mentioned, the extract and the raffinate phases. Now, liquid-liquid extraction is also called solvent extraction or simple extraction. Separation of one component from a homogeneous solution is by the addition of another insoluble constituent, the solvent, in which the desired component of the solution, the solute, is, the term used here is preferably soluble. So there is a preference, your solvent has a preference towards a particular component in your mixture, which is the solute. In this solvent, the solute diffuses at a characteristic rate until, again, the mention of equilibrium concentrations being reached in both phases. As an example, we can have here acetic acid, and this is a common, again, mentioned constituent in problems concerning extraction. that can be separated from an aqueous solution, meaning acetic acid in water, by contact with isopropyl ether. If you're going to browse through in Jan Kuplis and in McCabe, most of the problems there is extracting acetic acid using this isopropyl ether as the solvent. Although water is slightly soluble in ether, it has the role of refined, particularly insoluble. Now, solvent extraction is used to remove unwanted components from lubricating oils, so one of its many applications, and other fractions of crude oil to separate niobium from tantalum to produce concentrated phosphoric acid, and in many other applications. Now, I have here another video for liquid-liquid extraction. Okay. You will learn again the equipments that was shown to you in the video. Again, you will learn in SEPA because we will study them in detail how they operate. But nonetheless, you already have an overview of such operation of liquid-liquid extraction. Now we go to leaching, and it's referred to solid liquid extraction. So the component of a solid phase may be separated by selective dissolution rather, of the soluble part of the solid by an appropriate solvent. So this time we take out a solute from the solid matrix and we use a liquid solvent for that. This operation is also called leaching or washing. We call it washing if the solvent is water. Now the solid must be finely comminuted, meaning it should be like very, very small so that the liquid solvent comes into contact with it all. Usually the desirable component is soluble and the remainder of the solid is insoluble, and we refer to them as the inert insoluble solid. The solute must then be recovered from the extract solution in another separation step. Now, an everyday example of leaching is in coffee making. So, in this case, your soluble constituent of ground coffee are separated from the insoluble fines by solubilization in hot water. So, your solid matrix is your coffee ground or maybe not ground, but still it's still your solid matrix. Your solvent in this case is hot water. If the coffee is boiled for a very long time, the solution will reach equilibrium with the remaining solids. This is the time wherein we say that your coffee beans are already said to be spent beans. No matter how long you prolong the boiling of such beans, you will not be able anymore to extract flavor. The solution is separated in the strainer from the residual fines. Now, solid liquid extraction is also used industrially in the manufacture of soluble coffee to recover soluble coffee from sludge. Other industrial applications include the extraction of soybean oil, using hexane as the solvent, and the recovery of uranium from low-grade ores by extraction with sulfuric acid or sodium carbonate solutions. Because one of the phases is solid, it does not flow like a fluid. Special types of solid liquid extraction equipment must be used. Now, this is, I think, the last video that I will show because I have 3 more minutes. Hopefully, this will be done by then. What you just saw is the process of heat leaching. Again, we will learn that in leaching later on. You have a solid, and in this particular heap of solid, there's the introduction or the percolation of your solvent. The solvent that was collected, as you have seen in the video, is being collected in the form of a pan. And that's where I think in this case, since they are mining vanadium, that's where vanadium is being, shall I say, separated later on using several series of processes. Okay, now the last particular example that I have here for mass transfer is absorption. And I think in less than a minute, I will be disconnected already. We will just reconnect. It will not, I think it will not use up more than 5 minutes. So we will just finish that one and then you can have your quiz by 7 o'clock. Okay,